Guys, so today we're going to talk about trees and specifically binary search trees. So, first things first, a tree, generally, is a set of kind of nodes linked in a hierarchical fashion. So this is not a linear data structure, it is hierarchical. So there's some kind of generally starting place node. This is called the root node. And then this node might have what are called child nodes or children. And so those children, there might be several of them, but they are in turn nodes and they may have their own children. So you can see that this kind of looks like an upside down tree, which is of course exactly why it's called a tree. They may not have nodes. There may be lots of depth. There may be kind of branches that just kind of go off on their own. All of these things have kind of words that are associated to them. Not all of them are hugely important here. Worth noting is that when we talk about algorithmic complexity here, usually what we're talking about, the kind of n that we're talking about, is the number of nodes. Right, so in linear data structures, when we talk about the order of n for searching or inserting or something, what we mean is that n is the length of the list or the length of the linked list or whatever. In the tree, we're talking about the number of available nodes. There's some stuff that's worth noting that this kind of height of this thing is generally referred to as height. You will occasionally hear me say depth. That is what it is, I suppose. So this is generally a tree, something like this. It's maybe worth mentioning that you could, the kind of worst kind of tree is actually a linked list. Those are called degenerate trees for whatever it's worth. But in general, we don't spend a ton of time talking about trees. Usually we spend more time talking about what are called binary trees. So a binary tree is a tree where every node has at most 2 children. And then there's some words associated with this, like a binary tree might be complete or balanced or incomplete or unbalanced or degenerate. So what some of those words mean is this here is a complete balanced tree. Balanced meaning side to side it's balanced, right? And complete meaning that all of the nodes are filled. So this is an example of a binary tree. Here's another binary tree, right? They each have at most 2 children. This one, every node has at least one, or has just one child. This is an unbalanced degenerate tree. It is, in fact, complete, which is a bit odd, but whatever. So, most people, most of the time, in fact, in lots of YouTube videos, you'll find that people describe binary trees, and what they actually are talking about is what's called a binary search tree. So a binary search tree is a special kind of binary tree that has nodes with weights on them. So here's a binary tree, and this binary tree might have weights on the nodes. So it might have numbers in the nodes, and those might be something like, let's just say this one is 10 here. In order to be a binary search tree, the property that it must have is that all of the nodes in the left tree must be less than or equal to the node at the root, and the nodes in all of the right tree must be bigger than the node at the root. So what that means is that everything in the right subtree, this guy over here, has to be bigger than 10, and everything over here has to be less than 10. And then that rule needs to also apply to the subtrees. So, for instance, if this number is 8 here, then this number here could be 8 or smaller, because it's in the left subtree to 8. and this number here must be bigger than 8. Because it's in this subtree, it also must be smaller than or equal to 10. So this node here could only be 9 or 10. I'm going to put a 9 on it. I'm going to put a 7 here. I'm going to put 20. Oops. I'm going to put 28 in this node just for fun. And then this node can be anything smaller than 28 and also bigger than 10, right? So it can be maybe 15, and this one could be 87. Okay, the beauty of a binary search tree is that it lets us do what are called binary searches. So if I want to find something in this tree or establish whether or not something is in this tree, I don't actually have to examine every node. This is a lot like having a sorted list, right? You can kind of cheat the system a little bit with a sorted list. So if I want to establish whether 9 is in this tree, right, the very first thing I do is I consider 10. Right, I start at the root node. And because 9 is smaller than 10, right, I know that it's got to be on the left. Okay, now I look at the next node. The next node is 8. So 9 has to be to the right branch of 8. Ergo, it must be right here. If this number wasn't 9, I could stop looking because it ain't in here. Does that kind of make sense? So this allows for a nice recursive search that executes in O of log n time. So this is faster, right, than, say, an O of n search. So the binary search tree is actually quite a bit quicker and preferable in a lot of ways to our kind of linear data structures. So we're going to want to use these for some stuff. It should be noted that in order for these kind of optimal time estimates to happen, it has to be a balanced binary search tree. So as we add nodes to a search tree, we may need to go ahead and rebalance the tree. So you might find that these are, so search trees at least, are good to implement in cases where you do lots of accessing of data, but not necessarily huge amounts of changing data. Because if you're doing huge amounts of changing data, you're going to need to rebalance this thing periodically, which takes a little bit of computational power. That said, they are often used for these kinds of things with large amounts of data where searching is a priority and addition can be done. It gets done quickly, but then it needs to be rebalanced periodically. So this is nice for systems that have some downtime. For instance, I would imagine that a lot of DMV style lookups are done in a search tree like this because you add records to it, but you don't add them all the time. Like you add some records during the day, and then it takes the night off basically, so you can rebalance your tree overnight and then have it ready for lots of queries in the morning. That would be a good implementation of this kind of system. I can't speak to whether or not that's actually the system they use, but my guess is that it is. So in order to insert a new element into this, we would do something like, okay, let's suppose we wanted to insert, say, let me erase my red here. Let's say that I wanted to insert the number 14 into this tree. Okay, so in order to insert this number 14, the first thing I'm going to do is figure out where I want to put it. So I'm going to look at 10. It's bigger than 10, so it's got to go in the right subtree. You'll notice that this is just going to be a recursive method when we implement it. Okay, so I want to look at the 28 subtree, right? Now, 14 is smaller than 28, so it goes in the left subtree. So I look at the 15 subtree. This node with 15, it should be to the left of that. There is no node left to that, so I'll just go ahead and insert it right there. Suppose then that I wanted to also insert 13. Right? So if I'm also trying to insert 13, I'm going to say, okay, so it's right of 10, it's left of 28, it's left of 15, it's left of 14, ergo it must be here 13. So you'll see that if I'm inserting lots of data that's kind of sorted already, right? Like if I then inserted 12, right, 12 is going to also get inserted in here. You see pretty quickly I'm creating an unbalanced tree, right? This is why we might want to periodically rebalance the tree. There's a relatively easy way to do that. There's a relatively easy way to do that. It's not impossible, but you should have it in your head because it's kind of a popular interview question to talk about how do you rebalance these things. Okay, so that's what I need you to know for search trees. They are superior because they do tend to get done, or operations tend to get done a little faster with them. They can take up substantial space in memory if they're implemented poorly. So good implementation is kind of key here.